Glass half full says, I like you, but we're from different states. It'll never work. We cannot be together. Solid blue says, oh, but we can. Glass half full is still half full. That was your solution? Welcome to this video on concentrations of solutions. We're going to take a look today at what concentration of solutions are, how to make dilutions, and how to calculate each and every one of those concentration values that we're going to really need to have. So grab a writing utensil and someplace to take your notes, and let's get started. So the first thing is we want to know what a concentrated versus a dilute solution is. And we have concentrated solutions. They are the ones that we have a higher relative amount of solute that's dissolved in a solution. And then a dilute solution is going to be the opposite of that. In comparison, there's going to be a smaller amount of solute that's dissolved in the solution. Remember, the solute is the thing that dissolves, okay? So things like salt or sugar. And so a concentration that we're going to be calculating is really a measured value of the amount of solute that's dissolved in the solution. And we need to know about concentrations. We want to work with certain concentrations. We don't want to overuse our chemicals, especially in places where they would be expensive. And so we want to know what the concentration values are. So I think of concentrated as being something like concentrated orange juice. And so here we have some concentrated frozen orange juice. And if I want to actually make that into a dilute solution that's not so concentrated because, well, I don't know about you, but I don't think I could quite stomach quite that concentrated of orange juice. So we take that orange juice and we put it into some sort of a container and we mix it up with water. So we dilute it. We actually reduce the concentration of that in order to make a glass of orange juice. And so the concentrated form that we started with is our concentrate, and our dilute solution is going to be the glass that we end up drinking. And so that's just an example of something that we see in our life fairly frequently. So these are two equations that we're really going to focus on. There's some other ones that we might work with a little bit, but these are the two we're going to focus on. And so we want to be able to measure concentration in molarity, and we want to be able to also measure it in molality. And they're very similar words. You do need to know the difference between these. And so molarity we actually represent with a capital M, and it's going to be moles of solute divided by liters of solution. For molality, it's going to be moles of solute divided by kilograms of solvent. And usually our solvent on this is going to be water. And so we'll see that today. We will work in the solvent of water because we work with aqueous solutions. So let's try to calculate a few of these so you have some examples with you. And the first one that we're going to do is, or two that we're going to do, is molarity. So this one says, what is the molarity of a solution with 0.50 moles of potassium iodide in 750 milliliters of solution? And so we want to remember that our equation, I'm going to actually get a different color here. There we go. Our equation is molarity, okay, capital M, is equal to the moles of our solute. In this case, that's going to be moles of our Ki, okay, divided by the liters of solution. Okay. Well, we don't have this in liters, we have it in milliliters. For this, it has to be in liters. So we take our 750 milliliters and we can convert that into liters. We know that there are 1,000 milliliters for every 1 liter, and that ends up giving us 0.750 liters. All we really did is moved our decimal 3 places to the left. So you can use either method in order to do this. Okay. Now we plug our values in, and so we're going to take our molarity is equal to 0.50 moles divided by 0.750 liters. And when we calculate that value out, we get 0.67 molar. Should be 2 sig figs because this value had only 2 sig figs. Potassium iodide solution. So that is our value that we get. Okay. Let's try another one. We oftentimes aren't given just moles. We're oftentimes given grams because that's what we measure in. So we should be able to, oops, oh yeah, that was the right one. Here we go. We should be able to go from grams of our solute and liters of solution into our molarity as well. And so what we want to do here, same molarity equals moles of our solute. In this case, it's going to be sodium chloride divided by liters of solution. We have that in liters already, which is great, but we don't have this in moles. So if I want to find moles of sodium chloride, I'm going to take 98 grams of sodium chloride that we start with, okay, and I'm going to do a conversion. So for every 1 mole of sodium chloride on the periodic table, I add those up and we get 58.5 grams per 1 mole. Divide 98 by 58.5. This goes back to previously in the year, and we get that we have 1.675 moles. Now, this is a rounded number and I leave extra numbers. Please try not to round your intermediates too much because it can throw off your values sometimes. So be very cautious with that. So when I go to plug this into my molarity, I'm going to say I have 1.675 moles divided by my 3 liters, 3.00 liters of solution. And the calculated value for that in your calculator should come out to 0.558 molar sodium chloride solution. Okay, again, capital M there. So that is how we do molarity. Let's take a look at a molality problem. Okay, and so if we take a look at this one here, we remember that molality, so molality is lowercase m, that is going to be your moles of solute. In this case, we have sodium chloride again, so moles of our solute divided by kilograms of our solvent. Now, in this case, our solvent is going to be H2O. So we were given this in grams, and so we want to take that and go from 500 grams into kilograms. So there are 1,000 grams in 1 kilogram, and that gives us 0.500 kilograms. Okay, so, or you can move the decimal 3 places to the left. Either way will work just fine. So now what we want to do is plug our numbers in. So for molality on this one, we have 3 moles. Okay, 3.0 moles of sodium chloride divided by 0.500 kilograms. And when we calculate those ones out, we end up getting 6.0. Okay, 2 sig figs on this one, 3 on here. We're going to put the decimal place right after those zeros, and that actually will represent 3. So 6.0 molal. Okay. So little m in this case, I always put a little extra tail on my m to represent which one it is. We don't want to mix them up in the wrong place. Okay. We'll come back and use molality later on when we do colligative properties. So let's take a look at the last big concept for us, and this I think is one of the most useful things for me as a chemistry teacher. So we're making dilutions. I actually do quite a bit of this. How do you make a solution or dilution? So all of these things that I'm going over right now are probably the most practical things that I do in prepping labs. And so sometimes we'll start with stock solutions. So things like concentrated acids are usually in stock solutions. So we want to make a lower concentrated solution. I don't want to bring in 12 molar hydrochloric acid or 16 molar sulfuric acid into the classroom because that's pretty dangerous. So what we do is we actually dilute it down by adding some water to it. And the equation that we use is going to be M1V1 equals M2V2. Now, we need to know what each one of these represents. So M1 is the concentration of the stock solution or the original solution. M2 is the concentration of the dilute solution, so afterwards. So this is a before versus after, like we've seen before in other calculations with gases. The V1 is the stock solution that's used to make the dilute solution. So it's the volume of that. And this is where I always goof up when I haven't done this for a while. It's forgetting that that's for the stock solution and V2 is the total volume. So the V's are not equivalent to one another. And a lot of times people get confused with that. So make sure you're keeping straight which V's they are because this is the amount of the stock solution used and this is the total volume of the dilute solution. And so that's where if you're mixing chemicals wrong, it oftentimes happens in the volume. So let me show you an example of this. Let's take and say we have a stock solution here, okay? So say we have a stock solution. So here's our stock solution. And in the stock solution, we find out that this stock solution here is, let's see, we'll make it 10 molar, okay? So this is a 10 molar solution. Okay. And this is our original solution. So this is stock solution. And what we want to know is we want to know how much of this solution do we need to make another solution that's going to be our dilute solution. So our dilute solution is going to be over here, okay? And we're going to fill this up mostly, actually let me change the color there. We're going to fill this up mostly with water, up to about 90 milliliters with water, okay? Because we want to make a solution that is a fraction of our original one. So this is our water that we're going to add into this solution, but we only want to add 10 milliliters of the stock solution. Okay, so I'm going to take, this is our dilute solution, and we want a 1 molar. Okay, so this is M1, so M2 is going to be a 1 molar dilute solution. Now, what I need to do is I need to take, and if I want to make 100 milliliters of that solution, I need to take an amount of this and I need to transfer it. Oops, let me get that. We're going to transfer an amount here and get that up until we have the total amount. And so we want to know what the volumes of these are. So we're trying to make a total of 100 milliliters. So if this is 100 milliliters, and that's going to be my V2, we want to know how much of this we did. Well, remember we had 90 milliliters of H2O that we added to that, which means to get to 100, this part right here, our V1 that was transferred, had to be in the amount of 10 milliliters. 10 milliliters. And so we have 10 milliliters of our original solution added in with all of our water, and that's going to give us our 1 molar dilute solution. And so that's how we'll make these. We actually calculate them out though. So let's take a look at a calculation where we can actually do that. So here's an example. In this example, we see that we have a volume that we need to know from our stock solution, which our stock solution is 16 molars, a solution of sulfuric acid. So how much of that do we need to make 500 milliliters of 6 molar solution? And so what we want to do is we want to start off, and we know this here is my M1, okay? This here is my V2. I don't need to change it into liters, okay? I can leave it as milliliters. And then this one here is going to be my M2, and I want to know my V1. And that's a lot of times what I need to know. How much of that concentrated solution do I have? So we're going to put this into our equation. So I have M1 is 16 molar, and I'm going to multiply that times V2, and I'm going to then try to solve for this in just a moment. If on the other side I have 6 molar, and I have 500 milliliters. Okay. So now, in order to get V2 by itself, everything's being multiplied, so I have to divide both sides, and I have to divide them by 16 molar, okay, and divide this side by 16 molar. Those cancel on this side, and now to find V2, I'm going to take 6 times 500 and divide it by 16, So V2 ends up being 188 milliliters. So we needed to use 188 milliliters of that stock solution in order to be able to make 500 milliliters of total solution. So sometimes the question is, how much water would we actually need to use? Well, then you would take the 500 and subtract the 188 from that. So if we want to know how much H2O we would use with that, we would take the 500 milliliters and we would subtract from that the 188 milliliters. And I haven't done that yet because I just thought of adding that in here. So if we do that, 500 minus 188 gives us 312, and so that's going to be 312 milliliters of H2O that we had to add. And so all of these things are things that we actually use in making solutions so that we can use them for chemistry. I hope that was helpful.